Recently, my students and I built a PLC-controlled water pumping station. It's simulating a lift station of the type used in wastewater treatment systems. For the controller, we're using an Allen Bradley SLC 500 PLC mounted in this large control cabinet. The cabinet was donated by a local refinery. It used to be part of a boiler control system, which is why it says boiler number 3 at the top. However, we have taken all the old controls out and installed Allen Bradley SLC 500 PLC. Specifically, it's a SLC 503 processor, and we're using discrete inputs and outputs to control the statuses of 2 pumps. To control power directly to the pumps, we're using this pair of Siemens contactors with overload blocks here. The pumps themselves are submersible water pumps located inside this tub, and currently one of them is turned on. It's pumping water out of the tub up into a higher level reservoir. The idea being we are simulating a lift station, as you might see in a wastewater treatment system, where you have a local reservoir or a sump where wastewater runs from gravity from local businesses and homes into the sump, and a pair of level switches monitors the level of the wastewater. When the wastewater reaches the high level switch, it turns on a pump, and that pump then pumps to the wastewater treatment plant. The pump continues to run until the wastewater gets down to the low level switch, at which point the pump turns off. Now, just like a normal wastewater system lift station, we have 2 pumps. We have one redundant to the other. And what the PLC does is when it senses a high water level, it decides which pump it's going to turn on based on the one that's run the least amount of time. So the PLC maintains a pair of retentive timers that's measuring the on time of each pump. And the next start cycle, it looks at which pump has run the least, and it runs that one. So effectively, it alternates the pumps back and forth. Now, if for some reason the pump turns on, is not being very effective, and we retain a high level condition for a significant period of time, in this case program time of 15 seconds, the PLC decides to turn both pumps on simultaneously, which is a feature that would come in handy, let's say if one of the pumps were to fail. High level switch triggers, the pump doesn't come on because it's failed, and the high level condition persists. Then after 15 seconds it turns on the other pump. Thinks it's turning on both, but it turns on the other one. At least you have one pump running. At that point, we can also have the PLC flag an alarm and alert the operators as to the nature of the problem. So once again, we have a review of the cabinet here, our SLC 500 PLC system. We have another PLC right here which will be used for a future project on our air compressor. We're marshalling all the 120 and 24 volt wiring through a terminal block assembly there. And like I said, we're using a pair of Siemens contactors and overloads to control power to the pumps. Right now we've got the programming computer temporarily situated over here on a table, and we're looking at the program that one of my students designed to control this. He spent a couple days designing the system with less than or equal to comparison boxes and some retentive timers. There we go, we see a pair of retentive timers right there. And here's the high float on time. If the high level condition persists more than 15 seconds, it turns on both pumps. So he spent a little bit of time building this. Last night we got it programmed into the system for the first time, and we found a couple little problems. He diagnosed it and corrected the system. Now it's working just fine. So we're going to use this system now. We have it built. We're going to use it as a programming and troubleshooting platform for other student teams. Specifically, we're going to place real hardwired faults into the system. We're going to have students of different teams go in and diagnose what the fault is using the PLC ladder logic editor as a troubleshooting tool. By looking at the editor and watching the status of the contacts, we're able to tell what switch conditions are being made, which switches are not being made, and determine what the wiring fault is. Maybe not determine exactly, but give us good hints on where the wiring fault might be. So PLCs are powerful tools not only for controlling real processes, but also for diagnosing those processes they are controlling.